So we're going to cover genetic algorithms today. And the reason we're going to cover genetic algorithms is, and people could argue with me, but I think they're wrong. I would say a genetic algorithm is the most basic, not useless at all, but like your most general purpose evolutionary algorithm. It's going to cover all of the main points that any other evolutionary algorithm will more or less have. And because it's like so general, like there are other specialized forms of evolutionary algorithms, but a genetic algorithm is a great place to start learning. And I think the best way to get a sense of how evolutionary algorithms work is by doing. So seeing an example. Depending on how far we get today, so it might happen next week, depending on how far we get today, I'm going to show you, because you are going to have to do this in this class for your lecture and potentially your final project, is I'm going to do a little primer on using like GitHub. Raise your hand if you have GitHub experience. Okay, good. That's good. That's good. I'm still going to like show you. Now, typically the way I use GitHub is I do everything command line, but on Windows I think it's a little easier to use like there's like a program now, GitHub Desktop, that kind of makes it a little easier. So I'll show you an example of getting that, cloning the repo for the course, getting everything, and then running the code. I'm going to be using PyCharm for like everything. Maybe I'll use Colab every once in a while, but in general, everything is going to be using PyCharm. And I know last year some students ran into like some issues running their code if they were using different IDEs, like if they were using VS Code or something. Like they figured it out. I don't remember how. So if you want to use like VS Code.
I'm one of those people. I might be able to assist.
So if you get it working, then yeah, like just don't ask me because I don't know. That's a configuration problem. That's a you problem, not a me problem. So I will at least show you how to use like with PyCharm and whatnot. PyCharm, for those of you that don't know, it's a great IDE for Python. And most of this course, if not all of the content I have, is using Python. The only reason I'm using Python is for its ease for what we're doing, not because it's a particularly good language for evolutionary algorithms. It's just simple, I think, to use to show. Okay. So genetic algorithms. The purpose of this topic, do we have any questions before I get going? Did you think of anything from last time to ask today? All right. Oh, and by the way, some people, at least one person was saying they were having a hard time accessing the Moodle page, but it was shown. So keep checking because they said it just showed up eventually. So I don't know, maybe there's like a delay on their end. So if you didn't see it. What's
it? Been something with the Wi-Fi because I live at home, so I went home yesterday. It was completely fine.
Interesting. That's interesting. It could be like a caching issue with the old. Yeah, that's interesting. You could blame your browsers maybe, but good to know.
Explain it because when I checked it last
It was
week,
always here?
I was on data.
Okay.
So that could explain it.
Could be. Okay, so GAs. They're relatively simple. When I say simple, I don't mean trivial. I mean simple as like the opposite of complicated. And although simple, though, it's got all the necessary parts for your general evolutionary algorithm. And despite never seeing a GA before, I really think you're going to be able to follow along and get the intuition of all the parts. The topic after this one is a topic where I'll do a little bit of lecturing, but for the most part, I'll have you be like, you're going to download the code, make your own, get it working, so you can kind of see. So the first thing we need to use an evolutionary algorithm is, well, a problem to apply the evolutionary algorithm to. So we need to come up with a problem. And for the sake of demonstration, we are going to use a hilariously simple problem. It is a problem you wouldn't use a genetic algorithm for. It's silly. But it's a problem that's easy to understand. It's easy to know what's good and what's bad. And I think it gives us a lot of opportunities to think and ask questions about what the pieces would mean in the context of this particular simple problem. That can hopefully generalize to more complex problems.
Are you recording right now?
I think so. Yep. Thanks. It wouldn't be the first time I forgot.
Yeah, I remember one year you did it.
So here's the problem. Here's the problem we're going to solve. I want to find the biggest integer that I can represent with an unsigned binary number. All right? So find the largest binary representation, binary number representable with n bits, where n can be whatever. It could be like 10, 100, a million, whatever. But what is the biggest binary number we can represent with n bits? Now, obviously, we know what the best answer is. Whatever n is, just have n ones. There, biggest binary number, we're done. We don't need a GA for that. I know. But again, the point of this is to see the problem, see how the mechanics of the GA, genetic algorithm GA, how they interact. So what we would say here, this is going to be a common problem. I've tried to like boldface any like keywords, like jargon that comes up. A lot of this jargon is not restricted to, when I say jargon, I mean like terminology and words that have special meaning in our context. So when I say search space, but that's not specifically for genetic algorithms. That's basically any like search algorithm like machine learning, AI, optimization. Search space is a common word used. But a search space is, imagine you have a physical space. Like, let me put it this way. Let's say the problem was, find the warmest spot in this room. Okay? There exists a point in this room that is technically warmer than anywhere else. So the search space would be this physical space where I can go, right? Is it here? Is it here? Is it here? I could go through this space. So here the search space is all possible combinations of zeros and ones of size, of length n, where n is the number of bits we want to maximize. So we're going to be using n is 10. It's an arbitrary number. I just picked 10. So there is a lot of numbers that we can represent. With an unsigned integer, there's 1024 unique different numbers we can represent, 0 through 1023. So every single one of those is in the search space. We could look at each of those. Again, this is a relatively simple problem. We immediately know what the answer is. And a search space of size 1024 is hilariously small, right? You could easily iterate over every possible combination pretty quickly. But as you can imagine, as n gets bigger, that's going to become a problem. But still, it's a simple problem. Pardon me. So here is 4 examples. There is an n-length binary number, length 10, 10, 10, 10. They're all potential things that could exist in the search space, that do exist in the search space. They are in the search space. And if I were to ask you, how would you rank them based on goodness in the context of the problem, maximize the integer value of an unsigned integer, binary, how would you rank these? Any ideas? It shouldn't be tricky. Although there is kind of a catch, but we'll see it later. How would you rank these? Which one's better than, which one's the best, would you say? Whichever one has the most ones. What else could we use?
Has the farthest one to the left.
Has the furthest one to the left. Interesting. What else could we use? We're missing, in my opinion, the most obvious one. How would you rank these? By their value. In fact, rank them the way I did, right? That's perhaps the most obvious. We want to find the biggest integer number. So which one's the biggest integer number? The closer, if we find a number that's bigger, that's better, right? So that's how we'll think about this particular problem for now. So what we want to do is we're going to use a genetic algorithm to evolve bit strings, sequences of zeros and ones, to maximize the integer value of an unsigned binary number. When I say unsigned, let's just assume when I say binary number for this problem, it's unsigned, meaning there's no negative numbers. Like I said, we wouldn't use a GA for this, but we use things like computational intelligence, genetic algorithms for crazy hard problems. All right, so initialization. If we go back to that image I showed you last time that had like, what, 5 parts to it? Initialize, evaluate, select, and then genetic operators like change. You repeat that for however long you want until you decide to stop. So the first step is initialize. How can we initialize our algorithm? Well, the way we would do this, and it depends. Sometimes, well, maybe I'm getting ahead of myself. So before we can do anything, we need to initialize what we call a population of candidate solutions. A candidate solution would be something like this. A candidate solution is an admissible solution to the problem. It doesn't necessarily have to be the best one. Let me be clear. It doesn't need to be the best one. It is just an admissible potential solution, a candidate solution. So this is a candidate solution, this is a candidate solution, this is a candidate solution, this is a candidate solution. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 could be a candidate solution, and so on and so on and so on. So we create each individual thing is a candidate solution. In the context of this problem, a candidate solution will be a bit string of length 10. We could, well, again, I'm getting ahead of myself. Yeah, single candidate solution is a potential solution to the problem being solved, for example, yeah, like I just said. But how do we want to represent these candidate solutions? How are we actually going to encode it? Sometimes it's trivial to come up with an encoding, like this particular problem. It's a bit string. How could we encode it? How about a list of zeros and ones? A list of length 10. We could also use like literally a string of zeros and ones. That would work too. But let's just go with a list of zeros and ones. But there are some problems out there where coming up with a representation is really goddamn hard. Like, what would the good representation be? We'll see examples of those problems a little later. But sometimes it's not trivial. And we're going to talk a lot more about representation later in the course. But to give you a sense, like, we want our representation to match our search, like, well, the representation causes the search space. It has an effect on the search space. If I want to find the largest binary number of length 10, we really should only consider binary numbers of length 10, right? It would be silly to consider binary numbers of length 9 because if we have binary numbers of length 10, what is the size of the search space? Well, it's 1024, right? 2 to the 10. If we also included binary numbers of length 9, we would have an additional 512 things to add. And if we also included binary numbers of length 11, we would have an additional 2048 numbers to consider. So the search space is getting bigger if I consider more possible solutions. But we don't want our search space to be unnecessarily large. That's important. Again, this is such a simple problem, it might be hard to see, like, well, obviously it's stupid to include binary numbers of length 9. I know, but once we get to complex problems, this is a very challenging thing to think about. People can get PhDs defining a good representation for a problem. Like, this is a tough thing to do. We want our representation to be sufficient to represent all possible valid answers, all possible good valid answers, but we want it to exclude anything that's unnecessary. So binary numbers of length 9. So we want to make sure it's the search space, the representation allows for a search space that's big enough to encapsulate everything, including the best answer, but small enough as to, well, we don't want to spend time searching a larger search space if we don't need to. It should be obvious, but again, until we see a problem, it might not be that clear. So, okay, it is sometimes non-trivial to determine how a candidate solution should be represented. And here's an interesting nuance that most people that work in the world of evolutionary algorithms, they mix up their terminology a lot because everyone kind of knows what they're talking about based on the context. So I will point out, and I will make my best effort to be careful with my terminology. A candidate solution is would be like that binary string of 10 zeros and ones. A chromosome is an encoding of a binary, of the length 10 binary number. Candidate solutions are a solution in the context of what it means for the problem being solved. And a chromosome is how we've encoded that candidate solution. So the candidate solution is the binary number. The chromosome will be the list of zeros and ones. Cool? Yes?
In the case where the candidate solution isn't just ones and zeros, how do you encode?
We're going to learn all about different types of representations, but there are a couple of different, for fun, let's talk a little bit about this. And I'll give you, well, we're going to talk about I think the next topic is TSP actually. So I might be jumping a step, but, and this might include spoilers. Experiment. Okay, maybe we don't. Okay. So, okay. I'm not going to spoil the fun because I kind of like teaching this a little later. But here's what I will say. There are standard representations, let's call them, that can easily be used in a lot of situations. That doesn't mean they're the best ones to use, but they're maybe a good starting point. So this is an example of what we call a binary encoding. And if you go back in time, back to like the 80s, maybe even later, no, I think like the 70s, that was like the first encoding they used for anything, because you can encode anything you can encode on a computer, you can encode with binary. So just use binary to encode literally everything. As time went on, people were like, okay, that's a terrible idea. There is some advantages. There's something called like schema theory that shows how populations do convert. It's a whole thing. But there are things proven about the binary encodings that we can't prove about other encodings, but we know that in practice, the other encodings work really well. So this is a binary encoding. But let's say I want to encode, I'm trying to think of another problem off the top of my head, which is always a mistake. You can have an encoding that's just maybe something like a list of integers, depending on the problem, what that means. Like, how many of each widget should I take with me, where a widget is some arbitrary thing? How many pieces, how many widgets of each type of widget, how many of each type of widget should I put in my backpack for my trip today in order such that I make it the furthest? The widgets somehow make me go further depending on what they are. I don't know, right? So it could be some just general integer representation. Sometimes we have permutation representations where it's like an integer representation, but we never want to repeat individual numbers. I want an encoding that has basically a shuffle of 10 numbers, right? But the numbers have to be unique, right? So it can't be like 1 to 1. It would have to be like 1, 2, 3, 4, 5, 6, 7, 8, 9. They'd have to be unique. And then every possible permutation of those things. There are tree representations, but that goes into something called genetic programming, which is like my favorite thing. Genetic programming, where you're basically using a GA to evolve computer programs, which sounds crazy, but it works weirdly well. So, and we use crazy encodings for that. But sky's the limit. You can use whatever encoding you want, but there are some like typical ones that you think of when you go. but that doesn't mean they're the best ones. And as soon as you start to get into multi-dimensional problems where sometimes you're trying to optimize two things at the same time, and they might be in conflict with one another. Like let's say you want to maximize the size of the house you want to buy, but you want to minimize the cost. Well, those things are usually at odds with one another. So how can we optimize that? And that's where things can get really complex, but we've got strategies for dealing with that we will talk about later. Did that kind of answer? Cool. All right, good. So the chromosome is the encoding. A candidate solution is the solution in the context of the problem that we're actually trying to solve. So chromosomes exist in the search space. Candidate solutions exist in like the problem space. We'll see clear examples of this as we go. Again, this is such a simple problem and this is what we call a very direct representation. A direct representation, we talk about this later in more detail, but a direct representation is when the representation of the candidate solution is so goddamn similar that it's like obvious. But sometimes you end up having these crazy representations for these problems. So it's a less direct representation, indirect representation. Some people, like if you read through the texts that I recommend, some people like to talk about direct and indirect as if they're absolute, these like absolute terms, like that is an indirect representation and that is an direct representation. That's entire bullshit. There's like, everything's on a scale there. You can get more direct, less direct. To talk about these things as if they're absolutes, entirely useless, a waste of time. There's a lot of things that I am like a heretic about in the evolutionary algorithm world, but I can guarantee you I'm right and everyone else is wrong. But we'll cover them later. And I can show you really easily why I'm right. And we'll get there. All right, so for the integer maximization of an unsigned binary number, there are some obvious, reasonable, simple encodings. Here we'll use a list of zeros and ones. So the candidate solution is like that binary number, but it's encoded like this. I was saying before, chromosome and candidate solution, these words are often used interchangeably by the people, like as our jargon. They do have special meanings, specific meanings. They are different, but most people use these words interchangeably. And based on the context of what we're talking about, they know what we're talking about. I'm probably going to misuse the words technically because everyone uses them interchangeably, but I'm going to do my best to make sure I'm using the correct one. Like if you had 161 with me, I also talked about the difference. Like what's the difference between an argument and a parameter, right? By this stage, even though I definitely taught it to you if you took 161 with me, by this stage you've probably forgotten because you've misused and used these words interchangeably all the time. But they do technically have separate meanings. It depends on the value that you're passing to the function and the variable that the function has that takes on that value. But it doesn't matter. Yeah. All right, so a single chromosome can be created by, so how do we generate this random chromosome? Or how do we generate a chromosome? Well, we can just randomly generate lists of length 10 of the values of zeros and ones. You could, if given your problem, if you have some inclination like, I think it would be better if solutions, like I've got an idea of what a good solution would be. So you can like seed your initial population with like already good solutions to your problem. Again, with this simple problem, it's kind of silly to think about, but yeah, so you can seed it, you can generate them randomly, you generate the initial population really however the hell you want. That's going to be a big theme for this whole course. How do we do initialization? However you want. How do you do evaluation? However you want. That's really the takeaway. I'm going to show you popular ways, but at the end of the day, it's whatever the hell you want. Whatever's going to work. So a population is a collection of chromosomes. Look at that. I got it wrong already. It is a population of chromosomes, technically, because the candidate solutions are the decoded. Anyways, whatever. A population can be created by creating a list of randomly generated chromosomes. So if this right here is an example of an individual chromosome, I can have a list of some arbitrary length, a list of lists of zeros and ones. A list of chromosomes is a population. Cool. Cool? Yeah. Happy? Sad? You can make it a tuple for all I care. It just needs to be some collection of chromosomes. Each chromosome is randomly created. So below, here we go. Here's some code on how we can randomly generate a population. Assuming we have some population size value stored, so that's just some arbitrary thing. And bit string length, in our case, that's n, 10. So how big do we want the population to be? I don't know, 100, 1,000, I don't care. So we'll create an empty list. Again, this is just an example in Python. Use whatever language you want. Here's how I do it in Python, because I think Python makes it pretty easy. Create a population, do a for loop once for each thing we would want in the population, randomly generate a chromosome. This will do it for you if you used, if you're using like the random library in Python. Choices between 0 and 1, so it'll just randomly generate. It'll pick k values from here. We don't need to spend, if you don't believe me, test it out yourself. This will just generate a chromosome of zeros and ones of length, whatever we specify here. And then once it's created, add it to the population. Do it again, do it again, do it again. Just generate the population. This should be very clear. If this is not clear to you, we've got problems. Cool? Any questions? I shouldn't have deterred you from asking questions by saying you should know what this is, because if you don't, I want you to ask. The only thing that'll probably throw anyone off is the choices, but that's just an API call to, it's a library, it's from the random library that does what I want. If you like another function that can do it, go for it. Cool, there. Generates a chromosome, generates the whole population. Cool? Cool? Happy? Sad? Questions? Thoughts? Concerns? Musings? Anything? No? We're good. Good. I'm telling you, it's really not that complex. It's not easy, but it's not that complex. All right. Evaluation. All right. If we go back, and when I say go back, let me go here real quick. Whoop, I guess I clicked it twice. Like this is, here, I should do this, F11. Function F11, there we go, cool. This is an evolutionary algorithm. We did initialization, an example of initialization. I randomly generate zeros and ones. And if you think, well, could I generate that? Yes, you can do it however you want. I don't care. If it works, good. We use these things for their utility. The next thing we're going to talk about is evaluation. Okay, so I've got a population of candidate solutions of chromosomes. How good is each of them? So we're going to look at each chromosome and determine how good is it. So here's how we can do it. However, some will likely be better than others. Regardless, a mechanism for evaluating the quality or fitness, this is the jargon we use. And by the way, we steal a bunch of jargon from like evolutionary biology, but we butchered the meaning of these words when we took them. So like fitness isn't quite the same thing as fitness in the context of biology, but fitness is a measure of like goodness, a measure of like how good a candidate solution is. If something is more fit, it's more good. Bad grammar, I know. So the mechanism we use to evaluate the fitness of a chromosome, candidate solution, is what we call the fitness function. So let's just make, it doesn't have to be a function, but some way to measure the fitness. So the fitness is a measurement of a chromosome's goodness at solving the problem, a fitness function determines, it measures the chromosome's fitness. Cool? Yeah? Am I going too slow, too fast? Are you like, yeah, come on, get on with it? You're all happy. You're happy. Okay, good. Good. So here's an example fitness function. I'm calling it value fitness. It's got its docstring. If length is 0, okay, I've got an exception. Empty chromosome cannot be evaluated. Cool, whatever. Otherwise, well, this is a little Python-y, but this is a, okay, this is actually kind of like very Python-y. So what we're kind of, okay. So what we're doing, this is let me explain what it does. It converts, it measures the fitness by saying, well, what is the actual decimal value of that binary number, okay? That's what it's doing. So determine its binary value, but it's decimal because we're human and we like base 10. We have 10 fingers. It's awesome. How this works, I'm going to explain it, and if you're like, I don't understand, it doesn't matter. You can figure it out later if you really care. You could do it however you want, but this is an easy way to do it. Basically what this is saying is take an empty string and then append to it, join, the string version of the bit for each bit in the chromosome. So you look at the first thing, you append it to that string. Append to the string, append to the string, append to the string, append to the string. Then convert it to an integer. The comma 2 specifies it was a base 2 number, the string from base 2 to a regular integer. If that makes perfect sense to you, awesome. If it's clear as mud, it doesn't matter, okay? But that is a fitness function. It converts the binary, well really it converts the chromosome, the list of zeros and ones, into an integer that list of zeros and ones, when decoded back to the bit string, what it means, base 10, decimal. All right? All right. So that's how we calculate the fitness of one chromosome. Well, what if we wanted to do the whole population? Okay, well, obviously, I'm going to create another list that's going to correspond, that's going to be another list that's going to store the fitness values for each candidate solution. By the way, obviously, we can implement this literally an infinite number of ways. I'm just showing you one implementation. You could make chromosome objects that know their own fitness, whatever. I'm just going to have a separate list that has the fitness value for each, that stores the fitness value for each member of the population, and it's going to be index-wise. So index 0 in the population's fitness will be an index 0 of the population fitness list. Index 1, index 1, index 2, index 2. Cool? That's the idea? Yeah, happy? So population fitness starts as an empty list. So for each chromosome in the population, calculates its fitness value with the function, and then append it to the population fitness list. This should be painfully clear and obvious about what it's doing. If you really like Python, yeah, you could apply a map operation and calculate it if you like with lambda functions. It's fine. It doesn't matter. This is a little more clear to me. And remember, good code is code that's easy to understand. Just don't ask me to necessarily justify that one, because it might not be easy to understand. Any questions about the fitness function? Okay. The next thing, if we go back to here, is selection. So this is the part where, okay, look, we've generated a population, and we know how good each one is. Each member of the population, we know how good each one is. Now what we want to do is start thinking about, well, how do we pick? What strategy should we use for picking the ones in the population that are relatively less terrible than the others? How do we do that? Because we want to select them. We will apply variation operators too, but we want to select them and put them into our new population. But how do we pick them? And you might think well, obviously you just pick the best ones, right? Turns out that's a terrible idea. And we're going to learn why in more detail later. But so ideally, We want more fit solutions to be more likely to persist in the population. And I'm kind of using my words carefully here, because everything's going to be very probabilistic. We want less fit candidates to be more likely to die off. So more fit candidates, we want to persist in the population more than less fit. But there's a catch, because in evolutionary computation, there are two major forces at play that make evolutionary algorithms work. There are two major forces, but they're also in conflict with one another. The one force is how exploratory the search is. We want the search to be exploratory. We want it to be effective at traversing the search space to find good solutions. But if it's too exploratory, it's like too random. It's all over the place. So we want to guide it in some way. We want it to be exploratory, but we also want it to be exploitive, where it exploits what's good and what it knows to be good. So the exploration and exploitation are in conflict with one another. And we need to manage that conflict accordingly. If we always pick only the best solutions, that's very exploitive. But we lose the ability for exploration. We lose what we call diversity in the population. So we have to be careful. So like I'm saying here, it's not as simple as always selecting the best candidate solutions. Doing so would cause the population to converge too quickly. And with the example problem we're going to look at, we'll kind of see what that means. And this, if we converge too quickly, when I say converge, think of like every member of the population being effectively the same. They could be slightly different, but effectively the same. It's converged. And we've lost the diversity in the population. That's bad. So if we converge too quickly, well, that often, it says can result. It almost always results in suboptimal answers. So this is where it's important to think about the population, not individual candidate solutions. I know that, look, if we're using an evolutionary algorithm to find the best answer I can for this problem, I want to find the best one answer I can find in the problem. But yeah, individual candidate solutions are being evolved over time in the population. But really, the thing that we, as the programmers of evolutionary computation, and this is a thing a lot of people don't realize, so I like to emphasize it. It's important to think about how it's actually the population that's evolving. The population evolves together. And often we want to do things that benefit the evolution of the population, not the individuals. But that's always that balancing of exploitation, exploration. These are the forces that are always fighting against one another. Yeah, okay, so the fitness function is a metric of the ultimate goal, finding a candidate solution that best solves the problem, but focusing on this metric is to the detriment of the population. Instead, the population should emphasize diversity. But if we have too much diversity, we're going to include a lot of really terrible solutions in the problem. We need to balance the diversity, like the exploration and exploitation-ness. So this can be done. How do we do this? Well, like everything in evolutionary computation, well, what's the best way of picking the candidate solutions? However the hell you want. It really doesn't matter. There are two really popular strategies, one of which, probably the more popular one, by virtue of how simple it is to implement, is something called tournament selection. This is a great tool in your tool belt. You could do it however you want, but this is a common way to do it. Randomly select some subset of the population, select the best from that subset, and repeat that over and over and over and over and over and over and over again. And what's nice about this is how easy it is to dial in its exploitation and exploration. Let me put it like this. I have a population size of, let's say, 100. And then I'll have a tournament size of, let's say, 5. So I will randomly take 5 of the 100, okay? And of the 5 that I picked, I'll take the best one, okay? And then I take it and put it over here. Let's do it again. Randomly pick 5. It might be the same ones as last time. It doesn't matter. Just randomly pick 5. Take the best one of the 5. Randomly pick 5. Pick the best one of the 5. And repeat this process over and over and over and over again until you have 100 new ones. So 5. Why 5? Well, that was a number I picked out of nowhere. But think about what would happen if I increase the tournament size. If the tournament size, if the population size is 100, and let's say I crank it up all the way to the max. I have a tournament size of 100. I randomly pick all 100 and take the best one. Well, that's going to be the best one from the whole population.
100 times.
100 times, and I'm always going to pick the best one. Clearly, that's bad for diversity, but it's going to always pick the best one. It's trying to exploit. Yeah. Now, what happens if we dial down the tournament size all the way down to 1?
It's just pick a random one.
Well, now we're just randomly picking, and there's no what we'll call selection pressure towards anything more good. I'm just randomly picking 1, right? So when I pick 5 or 10, whatever, I'm taking the best one of that 10. So something that's better than the other 9 is going to go. If I'm just picking 1, I'm just randomly picking. So there's no decision I'm making based on what's better and what's worse. I'm just randomly picking. So with tournament size, tournament selection is great because it's simple to implement and it's really tunable. By adjusting the size of the tournament, we can adjust the exploration, exploitationness of our selection. It's great. So how can we do it? Well, here we go. Here's a function. It's going to take the population, the fitness values, a list of indices that were selected, and a direction. So the direction is, I'll explain it now, but basically you would change the direction to +1 or -1 based on if you're maximizing or minimizing. Basically, do you want to pick the solution with the highest fitness or the solution with the lowest fitness? Because sometimes sometimes you have a problem where you're not maximizing something, you're minimizing. So you can just change the direction easily. Anyways, for this, so I've got 2 exceptions. Okay, if the length is 0, well, you can't calculate the fitness of that. If any of the indices are out of bounds, well, you can't do that. Otherwise, max value, population fitness, selected indices 0. So this is just a linear search. Okay? Of the selected indices, look at each chromosome. This function does not randomly select indices. It gets a list of already selected indices. Okay? There's a reason for that. It's easier to test, and the dependency has been taken out of the function. That's a good thing. For those of you that don't know, here's an aside. When programming, if you have a function that depends on a library or something, and you're making calls to that library inside the function, that's fine. But if you can take it out and pass the value of something to that function instead of calling it inside, it's often better to eliminate the dependencies. You want to make your code as not interdependent as much as possible. So this gets the population's fitness, a list of length k, where k is the size of the tournament, that's going to contain indices that I've selected. So I start with index 0, and then I just do a linear search and look at each value at the indices that was given and pick the one with the maximum or minimum depending on the direction. And then when I'm done, copy over the population, or sorry, return the chromosome from the population at whatever that index was. Note, by the way, if you're not that familiar with Python or if it's been a while, this right here is an easy way to make a copy. So I'm making a copy. I'm not returning a reference to an existing chromosome. I'm making a copy of that chromosome and returning the reference to it. It's important. Very important. We don't want, we want it to be a copy. For any of this stuff, I know there's a lot of like Python-ness in it that can kind of throw you off a little bit. So don't get too worried about understanding this. I'm just showing you an example of how to do it. If you want to understand it, just take your time later. But basically, error checking, exception checking, do a linear search by assuming the one at index 0 of the selected fitness, or selected indices is the best one. And then do a linear search to find the one that's actually the best. Everyone happy, sad, confused, concerned, have questions, thoughts, anything? Your silence is concerning me because usually silence is a bad thing. Yes?
You said there were two most popular ways to determine fitness. What was the other one?
The other one, which we will learn about later, is something called fitness proportional. So to be clear, there's a lot. And of the a lot, there literally is. You could, first of all, you could do whatever the hell you want. But if you were to ask what are the most popular, it would be tournament and a fitness proportional one, where basically it's kind of like a roulette wheel. Imagine you have a pie chart where for each chromosome has a slice of the pie. But if that chromosome has a higher fitness, it's got a bigger proportion of that pie. And then you spin the wheel, or the whatever, and wherever it lands. So you're more likely to land on something with a bigger proportion, but you could land on anything. So that is another popular one. So what's neat about that one is it's relative to, your likelihood to pick it is relative to how good that one is, where with tournament, it's how good it is relative, it's just,
How good it is relative
Yeah.
to what it picked
Yeah.
and luck.
So here's what I've done here. So if I want to create a whole new population, I'm doing something, I'm creating a new list called the mating pool. It's not the new population list yet because we still have to apply variation. So I'm just going to take all of the ones that were selected. I'm going to do tournament selection 100 times, however big my population is, and put them into this mating pool list. So that's where I'm going to have the copies of the chromosomes. And then we're going to apply variation operator to it. So how are we going to do that? We'll create a list, and then for each thing in the population, do a tournament select, randomly select some number of indices, then do the tournament selection to get the one that we actually select, and then append it to the mating pool. Repeat, 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 repeat. Cool? Cool, cool, cool. To be clear here, I know this is the time, choice. This right here is where we're randomly selecting the, let's say k is 5, where I'm randomly selecting 5 indices that exist within the population, right? So the population size, if the population size is 100, it'll be 0 to 99. So this creates a list of 5 values in our example with the numbers between 0 and 99 in it. And those are the 5 that are in the tournament, and then the tournament selection part just actually looks at each of the 5 that were selected and picks the best one. I could have dependency injected. I could have put this dependency in, but I don't like to do that. That's not great for code and understandability and testability. So mating pool, the size of the tournament is defined by some hyperparameter called tournament size, and that's where we'll stop it. By the way, an interesting thing, does anyone know what the difference between parameter and hyperparameter is? All right, try to remind me to explain the silliness of this to you on Tuesday, whenever we have lecture next, whatever. Tuesday, cool. At 8:30, right? Yeah.